this one. Hello, everybody. I'm going to give you a talk about IME, Infinite Memory Engine. Before I start, it's always nice to get a sort of a gauge about people's background knowledge of IME. So put your hands up if you've been presented IME before and you've got some understanding. That's about half, I'd say. Okay, thank you very much. So firstly, just to give you a bit of a sigh of relief, a picture of some well-behaved puppies. There is kind of a little bit of a technical aspect to this. So obviously I work for a storage company, and quite often we deliver storage systems. And when we do that, we go through a tender process, and the customer says, yes, please give us a 100 gigabyte a second file system. And so we put it together, we deliver it, we install it, and then they run IOR. And what it does is it presents beautiful sequential reads and writes to the file system. You can see we've got a many-to-many process-to-file operations going on there. Everything's aligned, and everything's beautiful. And we pass the test, and the customer congratulates us, and then they go into production. And then, of course, what happens is the users get involved, and we see all sorts of I/O problems. We suddenly have many I/O processes to one bowl, let's say one disk or one file. We've got malaligned I/O, we've got random I/O, and we've got small I/O. And just one aspect of IME is about trying to cater for these real-world I/O patterns, which generally aren't the IOR benchmark. We're trying to cope with things like, as I said, random I/O, malaligned I/O, high thread concurrency, many threads talking to one file. These kind of applications of I/O and what applications do is really hugely distinct from the benchmarking process. So you've seen the large graph before, Robert mentioned it, and that's part of this slide. So this is a single rack system, 10 IME systems, and we achieve 550 gigabytes a second with IOR, with sequential writes and reads. The nice thing, though, is on the other side, we see this 50 million random IOs, so 4K IOs, writes, random, 50 million. It's a very, very big number for one rack. But right in the middle there, it's a fairly old graph, actually, but it really shows up what we're trying to do with IME. So if you look at the graph in the middle, which is sort of over the top of the rack, you'll see on this side, if you can't read, on the left side, we see 4K IOs. And then we increase the I/O size of this benchmark until we get 4 meg IOs or larger. And of course, the blue line there is what happens to the parallel file system. In this case, it was Lustre. And in fact, in this case, it was running SSDs. And what we're coming across is the overheads of this fully POSIX-compliant parallel file system. The red line above that is the IME performance. And you can see it sustains this extremely high wire speed throughput of that one's actually a small system, 40 gigaseconds it was at this time. But we sustain that right down to these extremely small IOs of 4K. And that can only really be done by a ground-up change in the way you create this IO system. And I'll give you a little secret about how that works. As far as IME is concerned, random IO looks identical to sequential IO. So we actually, when each of the clients, the IME clients are installed there, the applications perform lots of random I/O, we store that up in tiny buffers, and then we send it to the IME layer, and then we write it down to SSDs. That sounds like what happens in a file system, but there's many, many other steps in a file system. You've got to associate it with an inode, you've got data blocks on disk, you've got to read those into memory, you've got to update them and write them back before it's acknowledged. So we've really shortened that process and simplified the I/O process to give these kind of results which allow it to spread we can broaden the application I/O types that can be sustained at the peak I/O rate. So just a step back and talk a bit about IME for those half of you who really haven't been presented about IME before. On the left-hand side, you see a bunch of compute nodes, so a large supercomputer, for instance. And on the right-hand side, there's a typical storage system, a file system running GPFS or Lustre. And with IME, what we're doing is we're introducing a new tier. So in this case, we see the IME 14K. And a long story short, lots of details aside, this is an x86 system with some NVMe drives inside, and it's connected to the network. On these compute nodes on the left-hand side, not only have we installed the Lustre client or the GPFS client, but we've also installed the IME client. In fact, the IME client intercepts all the I/O that would otherwise have gone to the parallel file system, and it sends it directly into this burst buffer. And the burst buffer is behaving, as I mentioned before, it's not behaving like a file system at all. We take the I/Os, the individual fragments of I/Os, we buffer them up in the clients, and we send them and we write them down immediately into this NVMe layer. So you'll see on the red arrows there, there's these fragments of I/O. So we're dealing with fragments as they emerge from the application, and they're taken, buffered up, sent to the server. And then there's a process in between hitting the burst buffer and hitting the parallel file system where we try and tidy up that I/O. Because as we've already seen from the previous graph, a parallel file system such as Lustre and GPFS really doesn't appreciate these random small I/Os. So what we do in this burst buffer layer is we reorganize the random I/Os, and we sort them out into a parallel file system sort of staging area prepared nicely for the parallel file system behaviors, i.e. we try our best to create sequential streaming I/Os for the parallel file system. Just a slightly deeper look before we look at a benchmark we've run recently. So this is a picture of the IME client, and it's got an IME client piece of software installed. That's a red stripe there. And you can see a Lustre stripe at the bottom there, that's the Lustre client. And at the top you see a little dark stripe, and that's the application. So the application's issuing these I/Os, and the I/Os being intercepted by the IME client, and then they're being sent down to these set of burst buffer nodes on the network. One extra point though, whilst we're creating these data buffers, we're also creating these parity buffers associated with that data that we're trying to write. And then the parity buffers are being sent to different IME nodes, such that if we lose one node, then we can still satisfy I/Os that try and get that data. And you can see on the far right at the bottom there, we've got a number of valid erasure coding algorithms which we support today. So from 3.1 up to 7.1. And in fact, there's a broad, we can do 7.7+2 and 7+3 today. I mention this because it applies to the next benchmark we're going to look at. So this is a large system we have installed. We chose to use about 240 compute nodes. So these are dual socket x86 systems. They're connected by EDR, and there's a large burst buffer around 500 gigabytes a second attached to that system, that EDR network. Below that, today we have about 150 gigabyte a second Lustre file system. And so the compute nodes have a choice. They can either speak to the burst buffer and hit 500 gig a second with a nice IOR benchmark, or maybe something else, we'll find out. Or they can talk to Lustre and achieve around 150 gigabytes a second. To do this benchmark, you know, it's quite tough when you're doing benchmarking of systems this fast. You need an awful lot of I/O to demonstrate it. So is there anybody from Ireland in the audience? Anybody from Ireland? Owen, hello there. Hi. So Owen's from ICHEC. So him and some of his colleagues have been assisting us. They're kind of experts in weather, and we've been running this WRF benchmark. So WRF is a kind of popular open source mesoscale kind of simulation code, and it actually behaves, it's got quite nicely behaving I/O, but it can do quite extreme I/O in the right circumstances. Just before we move on, note that we're using IME erasure coding 7+1. So we're doing these benchmarks. We've got protected data. If we were to lose a node, we'd still be able to access that data, reads or writes. So the WRF config's there. I won't go into details, but essentially what we're going to do is we're going to pack these 240 nodes full of multiple jobs. They're going to run like in a real production system simultaneously. They're going to do both standard output, as in normal operation, and they're also going to do some serious I/O in the form of some checkpointing. And we're going to try that both to the burst buffer and to the Lustre file system. So here's a big plot. So here's the Grafana plot of what happens in real time as we're running the system. Starting from the left, there's time along the bottom axis, the x-axis, and as we move across, we see these very large checkpoint operations. The downwards yellow spikes are writes into the burst buffer. And you can see there's some very long spikes, so that's a checkpoint. There's some very smaller spikes, that's standard I/O. I say the smaller spikes, they're still 50 gigabytes a second from these applications. And then the larger spikes there are close to 400 gigabytes a second from real applications. You can also see this sort of stepwise sort of blue line going down there. That's showing the IME system filling up. But actually, if you look at the axis about filling up, this is consuming about 5% so far of the IME system. And by the way, while we're talking about filling up IME, it will hit a threshold by which it will automatically stage down to the parallel file system. And it'll hit another threshold by which clean data, which is copied down to the parallel file system already, will be then purged from the system to free up new space. So I mentioned that as just a little side, but the point is that users don't have to understand how this system is working. They don't have to move data between a burst buffer and a parallel file system. The burst buffer will manage that activity on its own. Okay, so this is the WRF on IME, 48 jobs running concurrently across 240 nodes, and we're hitting about 390 gigabytes a second. We do the same thing with a 150 gigabyte a second Lustre file system, and you can see immediately the peaks are rather broader, and essentially it's taking quite a lot longer. So here we hit 100 gigabytes a second. In fact, it's not bad. It's very well-behaved I/O, and we can just about see the peaks due to the checkpoints and differentiate them from the peaks due to the I/O there. This one's not too easy to see. It's a bit black, but hopefully you can see those blue lines I've drawn on. So these are the previous two plots, and I've just put them on top of each other and aligned up the x-axis, the time axis, so you can see what happens, the comparative throughput of this job, this complex high-throughput job, over time. And on the bottom axis, we're just talking about a few seconds, so this really adds up. And in fact, this code here, with many checkpoints in it and very high I/O load, the whole application runs 1.5 times faster. The I/O is, of course, about 4 times faster just from this application, even though it's doing very well-behaved I/O. So slightly more interestingly, this is what happens when we look at we kind of assess all the runtimes of individual jobs, and we stack them up in terms of how long they took. So let me interpret this a bit more for you. The red block there is showing you that every job essentially experienced a full I/O time for this checkpoint of about 4 seconds. Every single job in a very congested system with many jobs running simultaneously. The gray block with a long tail there is what happens when you run into Lustre. Some of the jobs get extremely fast access, essentially they go into cache, but many of them, and the worst, goes on for about 35, 36 seconds in this checkpoint operation. And so we see a much broader spread in the I/O times for those processes running on Lustre, and that's because we've got high contention, we're doing disk thrashing, we're exhausting the file system processes. So I kind of reduced this to a little bit of a table, and we've done this before in different ways, and it's slightly marketized, but let me talk you through it. So here what we're saying is we've got an application throughput for this application of around 400 gigabytes a second, let's say 380 on IME, and we're hitting about 100 on Lustre. And what we're going to do is just divide them by the metrics associated with those two systems. So the metrics are the number of rack units it consumes for the system, the number of I/O nodes in the system, the number of drives in the system, and the power consumption of each of these two systems. And what we find that per gigabyte per second, or we can get, let's say, 10 gigasecond per rack unit for IME, 21 gigasecond per I/O node in a system, about 1 gigabyte a second per drive with the application code, and about 14 gigabytes a second per kilowatt with this real-world application. And the Lustre numbers are around 10 to 20 times smaller. So the point is not that we can radically improve the application I/O and reduce the wall clock time, although that is true, but we've done it through a much, much smaller system with fewer watts, fewer things to manage, fewer rack units, and fewer drives. So in summary, just for that WRF run, we're going to do some more runs. So we're working with ICHEC so they are experts in more than one weather code, and we're going to try and dig deep and find the worst possible behaving code we can. So this is continuing, so there'll be more. But even with this well-behaved WRF code, we're seeing a huge reduced variance from about 36 seconds to 4 seconds by running on IME. We are seeing a significantly higher percentage of the peak throughput, i.e., we're running at 400 gigasecond on about a 450 gigasecond partition of an IME system. So that's nearly 85% of peak, whereas we're only hitting about 60% of peak with a Lustre system. And of course, that results in overall runtimes being about 1.5 times faster. So to conclude, I mean, we've got these systems now in production. We're running very, very large-scale real-world benchmarks. And it's kind of time to open this system up to customers who maybe haven't got the largest supercomputers in the world, but want to have a more mid-range system. And to do that, we've introduced this IME 240. It's 2U high, it's 20 gigabytes a second, and it really helps us trying to reach out to customers beyond those top 10 customers in the world and help this IME burst buffer approach, let's say, more universities and research systems around the world. My time's up. Thank you very much.